last class, right? We talked about already several of the processes that are involved in the formation of planetary systems. The growth of the dust, the first class, how to form the first planetesimals for discriminant instability, that was the second class, and then how you grow these planetesimals into cores by pebble accretion, that was a class that we had last time. So today, let's talk about what completes the formation of planets. Let's talk about another mode for the formation of planets, which is vortex trapping, and also the formation of giant planets. I'll touch upon how these can be generalized maybe to even planet formation around population 2 and 3 stars, since we have only been talking about methods that can form planets at very high metallicity, but there are these two modes that can maybe also work for low metallicity disks. And I will touch upon the AGN channel, which is essentially scaling up these ideas also to other types of disks in the universe. So first things first, let's talk about vortex trapping. What do we mean by that? What is a vortex? A vortex is a long-lived concentration of vorticity. So that's a circular definition in here. So what would be a non-circular definition? As you see here, it's a patch of coherent vorticity. It's a patch of, essentially a patch of constant angular momentum in the disk. What you're seeing here is a model where you're seeing the density, here is plotting the vorticity. The vorticity, by the way, is the curl of the velocity, right? Call it omega, so omega, that's the vorticity. You take the curl of the velocity field. So it's, if the disk is rotating in this way, the vorticity is pointing upwards. So it's a patch of constant angular momentum in the disk. And from all we saw already about how dust moves in protoplanetary disks, the dust grains are going to move towards regions of high pressure. This vortex traps gas, as you see here, forms a region of high density, and therefore also traps the dust. So it's a way to concentrate dust grains. This idea was proposed already back in the 90s. On this paper here, it was proposed that if you have a vortex somewhere in the disk, if you are a dust grain, so these are two trajectories here of dust grains, A or B. So a high impact parameter, a lower impact parameter, you would, this dust grain would enter the vortex, and because it is also suffering gas drag, it will move towards the center. Essentially, it's the same process that is happening to the dust grains in the larger disk. You have the drift of the dust grains towards the star, right, because they're suffering gas drag. And in this case, the same thing is happening, except that in the center of the vortex, there is no star to burn the dust grains up, so they just concentrate more and more. It's a very convenient effect to them that can raise the dust-to-gas ratio locally in an extreme way. The vortex streamline itself is in equilibrium between the Coriolis force and the pressure. As I said, in the disk, right, you have a centrifugal balance between the gravity of the star, the centrifugal force, and the pressure gradient. Here's the same thing, but instead of the gravity from the star, you have the Coriolis force, right, is pointing towards the center of the vortex. But the rest is pretty much the same. So the dust grains are going to get into the vortex, and because they are not subject to the pressure force, what they're going to feel is going to be just losing angular momentum because of the gas drag. So you see here, this is a simulation that there was a vortex in the gas phase, and the dust grains are concentrating more and more, right? The grains do not feel the pressure gradient. They just sink towards the center where they accumulate. So this is going to aid the planet formation, and it's going to speed up planet formation by a lot. In this model here, the trapping of the dust grains quickly achieves the critical densities for gravitational collapse. This model here did not have self-gravity, so you're not seeing the formation of planetesimals yet. But if self-gravity was switched on, it would have happened. Here we measured the dust-to-gas ratio. So this is the vorticity in the gas phase. It easily achieves dust-to-gas ratios beyond 1. Right? So if the dust-to-gas ratio goes beyond 1, That means that now it is not the gas telling the dust what to do, it's the dust telling the gas what to do, right? The dust becomes dynamically dominant. Streaming instability might kick in and then form planetesimals out of this flow. And you see here that the grains to gas ratio. So 1 would be around, I have to move sideways to see this. You would be around here, so the yellowish part. So these very bright regions are regions where the dust is concentrating a lot. And as you see, these are coincident with regions in that the gas is being strongly perturbed by these very high concentrations of dust grains. Good, so it seems that we have a method here to form very high concentrations of dust. What would happen if we have self-gravity included in this calculation? This is what I'm showing here. So this is a model where you can see this vortex, this giant vortex in the gas phase. These are 3 snapshots at 2 orbits after we inserted the dust grains. So 5 orbits and 12 orbits. This is the vorticity in the gas, the pebble column density, and here in these white dots, there are planetesimals, right? These are planets, planetary mass objects that are forming because of the dust is being trapped here, right? And soon they are collapsing and then forming objects. And as you see, in only a few orbits, you are forming planetary mass objects all over the place. Now, why am I calling these planetary mass objects, since I've been saying planetesimals in the past classes? Because when you measure the masses of these things, it turns out that they're extremely massive. These are not planetesimals that are being formed. Look at the masses here, right? This is in units of the mass of the Earth. What you're seeing here is 3 different simulations, right, where these are being formed. So this is the lowest of the resolution run in green, the medium resolution in orange, and then in blue here, the highest resolution that we ran. So this is the mass, and here the mass function. What you're looking here is the initial mass function of the objects that are being formed inside this vortex. There is a convergence here, right, with a resolution. This is the cumulative mass function. What you see is that you form a few Earth mass objects. You form dozens of Mars mass objects and hundreds of Moon mass objects, right? The convergence here seems to be quite good. Now, how can we verify this vortex trapping hypothesis? Of course, the proof is in the pudding. The ultimate arbiter of theory are the observations. So let's look if we see a hint of this process happening in actual observations of protoplanetary disks. These are 2 different disks. This is the disk around the star Ophiuchus IRS 48. This is an observation with ALMA in millimeter grains. And this is the disk around the star MWC 758, also an ALMA observation. What you're seeing in both cases is a huge non-axisymmetric concentration of millimeter-sized grains all on one side of the star, right? So this is a telltale signature of vortex trapping. Not saying that these are categorically vortices, but they have all of the properties that we expect from vortex trapping. So if something walks like a duck, quacks like a duck, might be a duck. This was from 2013. Was heralded as a huge vortex observed with ALMA. In the paper itself, they were a bit more cautious about calling it a vortex. They called it a major asymmetric dust trap because that's what is seen. But the physics, if this is a vortex, the physics that is trapping here is simple. We have the drag force that is trying to bring the dust grains inwards, and then the diffusion that is trying to kick the grains out, right? The diffusion, as we saw from the previous lectures in this course, comes from the turbulence that is happening in the disk and in the vortex core. If this dust is being observed, is because it is in a steady state. The steady state is between the drag force and the diffusion. So we can solve then what the continuity equation for the dust grains will be. The terms you have here, essentially what you do is that you cancel the left-hand side, right, for the steady state, and you have these three terms here: the advection of the dust grains, compression as they move inwards, and then we had to add an extra term here for the diffusion, parameterize the diffusion. And this, we can solve it analytically. I'm not going to go through the math because there was 10 pages of equations to solve that, but in the end, this is what we found. That's the steady state solution of the dust grains that are being trapped here. We found the analytical solution in terms of the 6 quantities here. You can combine them and then define the solution in terms of these 3 quantities, which is the aspect ratio of the disk, right? Remember that quantity, the scale height. Chi here is the aspect ratio of the vortex itself, in this case 4:1, so 4 times more elongated in azimuth than in radius. And this quantity S here, that appears a lot in when you have drag and diffusion, which is measuring the Stokes number over the RMS of the disk, right? Both are non-dimensional quantities. This is measuring the size of the dust grain, and this is measuring how strong the diffusion is. So we have this solution here in terms of two Gaussians in radius and azimuth. Well, this matches the shape, right, of the emission that is seen here in this disk. This is the observed intensity. This is a modeled intensity, and this is our solution in terms of trapping these grains in vortices. So it seems that, yeah, we can explain in Ophiuchus IRS 48 what is happening. And now you can apply the same model for MWC 758. In this case, here you have two vortices there in the disk. Now, one thing that is interesting is to see then how the trapping happens if we apply this model to different dust grains. Because different dust grains are suffering, are subject to the gas drag in different ways. What you see here is that for the smaller dust grains, right, so small Stokes number, the size of the trapped dust region is going to mimic more the extent that you see in the gas phase. So what you see here is this. This is the vortex in the gas phase, small dust grains, not so small dust grains, and large dust grains, right? So the large dust grains, they decouple partially. They are quite mobile. They are all going to concentrate on a single point there, right, very strongly. The larger dust grains, they are more subject to diffusion, so they concentrate in a more extended region. So we can see that if we perform multi-wavelength observations, because in different wavelengths you are observing different grains. In ALMA, which is millimeter wave observations, you're looking at the millimeter size grains. If you use VLA in radio, you are looking at centimeter and meter size objects in the disk. So this is an overlay. I like to call this disk tomography, right? So sphere is observing in infrared, so that's micron-sized grains. The micron-sized grains, they are very well coupled to the gas, right? So you are looking only at the surface of the disk. You're not looking at the mid-plane. Infrared is very opaque. So as you see here, the infrared are the black smudges here. They are doing something else completely different than what the large grains that settle to the mid-plane do. So in the mid-plane, you have here in red the VLA, right? So these are the centimeter-sized grains, and in blue the ALMA. These contours here, if we look at only the ALMA and VLA now, the grains that are settled in the mid-plane, this is what you see. You see that the ALMA concentration of grains is larger than what is seen with VLA. If you overlay them both here, this contour is the contour of the ALMA observation, and in red here, the contour of the VLA. This is exactly what you expect from the models, right? The larger grains, the ALMA grains here are more extended, And the smaller grains are more concentrated, and the large grains here, the ones that are seen with VLA, they're less concentrated. So it seems to match. Right, so it seems that what is happening in this disk indeed is vortex trapping. And this model shows that inside this vortex, you are producing planets, right? Planetary mass objects, right? As I showed before here, hundreds of moon mass objects are being formed in there. Now, this model here is for a disk with a slightly more metallicity than the sun. Though the Z value used here was a few times 10 to the minus 2, so 3 times 10 to the minus 2. So it's even more metal-rich than the sun. But in this figure here, we're showing what happens if you relax that. So this is the dependency on the objects formed. So we're showing here on the x-axis, that's the time, and on the y-axis, the concentration of dust grains, right? The maximum dust density that you achieve. The Roche density in this model is close to 90 in these units. So the Roche density is the critical density to bind these objects, right? To gravitationally bind these objects, the density by which the self-gravity of the dust grains becomes stronger than the gravitational tide from the star, and you have a gravitationally bound object. So you see, you easily achieve that in these models. I have Stokes number 0.3, so close to the dynamical time of the disk, and solar metallicity here, 10 to the minus 2, right? And this here, we vary the Stokes number, keeping the same metallicity. So for smaller grains here, 0.03, you end up not achieving the Roche density. So you would say, wow, okay, then objects will not form. However, it easily goes beyond the dust-to-gas ratio 1. Now this model here, the resolution was not enough to resolve the streaming instability, but the idea is that if we had the resolution, once you cross the dust-to-gas ratio 1, the streaming instability would be triggered, and you would be able to form planetesimals inside the vortex, right? So it's not through direct gravitational collapses in this case, but then an indirect route. So in a way, the vortices can boost the local dust-to-gas ratio to reach the conditions for streaming instability when you otherwise wouldn't be able to have that present. And more importantly here in this last plot, we changed the metallicity. So from solar metallicity, 10 to the minus 2, which is the gray line, to 10 to the minus 3, so 10 times less metals than the sun. That is the cyan line. That the vortex itself is able to concentrate these dust grains to achieve direct gravitational collapse. However, as you go to 10 to the minus 4, the same thing that happened here for the Stokes number 0.03 case happens, right? You don't achieve Roche density, so no direct gravitational collapse, but you can easily achieve dust-to-gas ratio 1. So for metallicity 10 to the minus 4, the streaming instability alone would never be able to achieve the conditions for it to operate. Remember that plot that I was showing on previous lessons here in this course, that this is what the streaming instability does by itself, right? This plot here in terms of the Stokes number and the metallicity. You can barely get streaming instability for solar case, but already for 10 to the minus 3, you cannot, right? Seems that with a vortex, you can achieve direct gravitational collapse at metallicity 10 to the minus 3, and you can give a boost even at the metallicity 10 to the minus 4, so that locally, in some small areas of the disk, those areas with vortices, you can cross into a local solid abundance of 1. So you jump from this pink region of the diagram to the green one, and then would be able to produce planetesimals. So I'm calling this vortex boost. Right. Another thing that you notice is that there is almost a similarity here between the Stokes number 0.03 and metallicity 10 to minus 2, right? The green line and the magenta one. You see how similar they are? Well, that's not a coincidence, right? Because we can measure here from that analytical solution that I showed you, right? What the maximum dust density will be, right? This is an exponential. The maximum that this exponential can get here, because there is a minus sign, is 1, right? This is normalized. And then, so this one will give you the maximum density. So that is the vortex boost that I was talking about. There you go. If this region, if this quantity here, the left-hand side quantity reaches 1, or I mean, if it goes above 1, then you can trigger this Riemann instability. If it goes to 90, then you have a direct gravitational collapse. So you see here, this is the metallicity, again, and that quantity that we talked about, right? The Stokes number versus the non-dimensionalized RMS of the turbulence. What you see here is this quantity here, right? The dashed line for these different combinations of metallicity and Stokes number. So this is a simulation with vortex trapping. What I'm showing here is the maximum density threshold, and then the diffusion, right, that goes into this delta here. In this case here, this delta quantity and this alpha, they are the same quantity, right? And an average of all of the grid cells in the simulation that had the density higher than this density threshold. So what you see here is that for the models where collapse happened, the diffusion was always lower than the threshold, right, for collapse. So this is density 90 here. So the very right-hand side of the plot is the critical density, right? The Roche density. Now, the models that did not collapse are the magenta line and the green line. And as you see here, the maximum density on both cases is consistent with the prediction from this equation. So we can use then this boost to predict even in a low metallicity gas if the conditions for planetesimal formation would be present. Maybe this is something then that we can use to predict if a planet formation will happen in POP2 and POP3 stars. Yes? Sorry?
My comments about this metallicity, that is still a POP1, right? Because it's 10 minus 2, it's not a POP3, let's say. It's probably limit POP1.
Yeah. So if I'm understanding the question is, the typical metallicity of POP2 stars and POP3 stars are much, much lower than even this extreme value here. So Z 10 to the minus 4 would be equivalent to metallicity iron over hydrogen, right? Minus 2, right? So this shows here that this would easily achieve dust-to-gas ratio above 1 for a disk around a star of metallicity minus 2. Now, if you want to go to POP2 stars, then we're talking about what, like minus 3, minus 4, right? Yeah. The lowest simulation that I ran was 10 to the minus 4. It would be interesting indeed to see what would happen for 10 to the minus 5.
5, exactly.
Which would be metallicity minus 3, right? But what I'm showing here is that this equation can reproduce, right, what the model sees. So we're talking about a combination, finding out for a typical Z, what is the combination of grain size, the Stokes number, and turbulence, the delta, that would bring this quantity here above 1, right? Okay,
Thank you.
thank you. Right? Cool.
After streaming instability kicks in, does it help or does it compete with the vortex formation?
Very good question. Give me a year and I'll answer that. We still need to model it. But yeah, excellent question. Like your question could be a PhD thesis.
Not yours. You're already doing something else.
Right. Right, so conclusion here is that we have two routes for planet formation. We have streaming instability and we have vortex trapping. Right? They can be competing or complementary. Right? Next then, the next rung of the ladder is, if we now form the rocky planets, how to form the gas giants. Right? So there are two hypotheses here for the formation of gas giants. One is just continuing core accretion. You formed the rocky planets, and these rocky planets can act as seeds for accreting the gas and then form a gas giant. The other one is gravitational instability, also called disk fragmentation. So on the first one, I like to call it a bottom-up approach, right? You start from the core, you start building the small things, right? The planetesimals, and then the rocky planets, they get big enough to form the core, and then they accrete the gas. While this one, I like to call it a top-down approach, because what is going on is a direct fragmentation of the gas itself. You're forming a planet, in this case, in the same way that you form a star. Right. So these are the steps here for the core accretion, right? You form the dust coagulates into the pebbles form planetesimals through streaming instability, and then you have here the planetesimals accreting the pebbles to form rocky planets, or you could have the planetesimal accretion by itself also to form the rocky planets. Or you can have the pebbles directly forming the rocky planets, right, through vortex trapping. And then once you have the planets, then for gas accretion, you can form a gas giant. The other route is the direct gravitational instability of the gas, right? So the gas overdenses, they collapse. So how does this process happen? What is the physics happening here in this process? The main ingredient here is something that we haven't talked much yet about, which is the self-gravity from the disk. Right? The gravity from two gas parcels in the disk. Right? Gravity, of course, is always present. We haven't talked much about it because so far I considered only low-mass disks, so you can ignore the gravity from the gas. But if the disk is massive enough, then the gravity from the gas will play a role, just like it plays in galaxies. Now, the quantity that is that will determine if the gas will be collapsing or not is this quantity here that is called Tonry Q. Right? The Tonry Q value is measuring here the relative importance of these three processes. So gravity is what is trying to make the gas collapse, and what is trying to resist the collapse is the pressure from the gas, right? As you compress gas, it heats up. So then you build up the pressure, and then it will try to stop the gravitational collapse. So collapse will only continue if gravity is stronger than the pressure, right? And in the disk, there is another process also, which is the shear, right? The gravitational tide from the star. Shear prevents collapse because if you have a blob that is trying to concentrate, this side of the blob is trying to orbit in this way, and this side is trying to orbit in this way, right? So if the gravity is not strong enough, shear is going to win, right? And you shear away the blob, and it's going to be dispersed. So to achieve gravitational collapse, gravity has to win against both of these two processes, against both pressure and shear. So this Tonry Q quantity is exemplifying this, is embodying this. On the numerator, what you have is the sound speed and the Keplerian frequency. The sound speed here comes from the pressure. The Keplerian frequency here comes from the shear. And on the denominator, you have here the gravitational constant, right, and the density, so that's the gravity. Essentially, what this quantity is here is pressure times shear divided by the gravity. So if this quantity is below 1, that means gravity wins, and then you have instability and gravitational collapse. This is a gravitationally unstable model. So this is how a disk that is unstable will appear. This is not a protoplanetary disk, which you can see by the scale here in kiloparsec, right? And the time here in mega years, in giga years. So this is actually a galaxy. Right? A gravitationally unstable protoplanetary disk looks like a mini galaxy. You have the spiral features in pretty much the same way. This is a low mass disk, right? 5% of the mass of the star. 10% and 25%. You increase the mass, you widen the spirals, as you see here. This is a simulation here where it is measured the Q value as a function of radius, right? The Tonry Q value as a function of the radius of the star. And what you're seeing here is this Q here, right? So the value of Q. And approaching 1 here in the outer parts of the disk. As you see, the inner part looks stable, right? It is not developing spiral features. This is the region here where the Q value is bigger than 1, so 2, 3, and 4. And it's the outer parts here where you have the spiral arms where the Q value is closer to 1. Right. So again, what this Q value here is doing, as said, is measuring, right, the relative importance of pressure and shear against gravity. If you do the analysis of this, if you work out all of the math about how this works, you will be able to plot this diagram here, which is giving you the complex eigenfrequency versus the wave number. We call it a dispersion relation. Now, this complex eigenfrequency here, as you see, is a squared. Whenever this quantity is negative, that means that you have instability, right? If it is real, you only have oscillations, right? Because this is e to the power of minus omega, right, minus kx. Yeah. So if this quantity, this is not the same omega, by the way. That happens often when you do F. So instead of, so let me erase the vorticity here. The omega here is a complex eigenfrequency, right? This is the behavior of a single mode, right? A Fourier mode, a wave. As you see here, if omega is real, right? If omega is real, that means if omega squared is bigger than 0, you only have oscillations, right? Things are just going to oscillate because this is exponential of minus I. That's just sines and cosines. However, if you have that if you have that omega squared is less than 0, that means that omega is imaginary, right? Or at least has an imaginary part. So this omega here being imaginary is going to contribute an I, right? And then you have minus I squared becomes positive, and then you have something that grows exponentially. So that's instability. So let's give it an exponential growth. So this case here, these are just oscillations that's stable, right? A mode that doesn't grow in amplitude, Whereas in this case here, if you have exponential growth of a mode, what is growing exponentially is the amplitude. So you have growth, so this is an unstable situation. This plot here is showing where you have stability and where you have instability. So this line here, the red line is 0, right? So above that, omega square is positive and you have stability. Under it, omega square is negative, right? So then you have instability. The modes will grow. And this is what the three terms here, what these three forces are contributing. This is the contribution from pressure, as you see, is always stabilizing. This is the contribution from rotation, which is, again, is stabilizing. And gravity here has always a destabilizing contribution. If gravity wins, then you have instability. And as you see, it happens only in this small part here of the diagram. But all that it takes is a single part, a small part, it doesn't matter how small. If any part of this black curve here, which is the sum of these three lines, goes negative, there is a region of the system that will go unstable, amplitudes will grow, and you'll have instability. Let me show it again here. And yeah, so that's what you're seeing here in this calculation. There are some regions where the Q value goes below 1, right? That means that the quantity, omega square, is going negative. Now, this quantity Q, right? We can see here what is the mass that is going to form if this quantity goes below 1. So as you see, it doesn't actually get much below 1, so let's make the approximation that this is about 1. And for the typical speeds in the disk, so the sound speed, right, is about 1 kilometer per second. So that's 10 to the 5 centimeters per second. I like to work in centimeters because I'm an astronomer. So omega, let's say that we are at 1 AU. So omega here, so you put here 2 pi over tau, and the period would be 1 year at 1 AU. The typical densities in these massive disks would be a little more than the minimum mass solar nebula. So let's give about 1.5 times 10 to the 3 grams per cubic centimeter. Put these numbers here, the sound speed, omega, and sigma, right? That's then what you get for Q equal 1, right? If you have Q equal 1 here, that gives you then this density. Now, the critical mass then that will form will be given by the area, right, of the unstable wavelength that will collapse. So that's the cross-section, pi r square. In this case, r is the critical wavelength, times then the column density. This column density here that comes from setting Q equal 1. Now, the lambda comes from the critical K, from the critical wave number, which is this Q here, the Q of this part. If you solve this, you would find that the critical K, the critical wave number, is about pi times G times sigma over CS squared. So that K here defines what the wavelength is, because the wavelength is 2 pi over K, right? So you plug in here with these quantities, and you find that the critical mass will be about 5 Jupiter masses. So a gravitationally unstable disk in the regions where the Q is equal 1, for this combination of parameters will produce gravitationally unstable, like gravitationally bound objects of mass about 5 Jupiter masses. So let's look at the population of exoplanets and see if there is evidence for this. What we're seeing here is what? The planets that are found I mean, all of the exoplanets that have been found by method of discovery. So the red dots are the planets found by transit, right? The red ones, radial velocity. There are some planets found by macrolensing here in purple. What I'm interested in here are the massive planets, right, that are further out. So there will be this region of the diagram here that is populated by the planets discovered for direct imaging. So these are planets that can be seen. And as you see, they are on the massive side and on the further outside, which makes sense, right? These are the easiest ones to detect. The prototype of this type of planets are the planets around the star HR 8799. What you're seeing here is Kepler's third law in action, right? Remember that if the planet is closer to the star, it's going to move faster. If the planet is further out, it's going to move slower. So that's Kepler's third law here, seen in real time in 4 planets around that star here, the planet B, C, D, and E. And each one of these planets turns out to have about 7 times the mass of Jupiter. The orbits are regular, as you can see here. So this could be planets that are formed via gravitational instability. It is not, I mean, we cannot say for sure that they were formed via gravitational instability, but 4 massive planets in the same system, 7 Jupiter masses each, it seems to fit quite well with what we expect from the masses of planets that should be formed via gravitational instability. Another telltale object that could be formed via gravitational instability is AB Auriga. AB Auriga is this object here. So this is an image from Hubble, and we claimed back in a paper in 2022 here that this is probably an object that is caught in the process of formation via gravitational instability. This is AB Auriga B. So AB Auriga has been imaged in several different wavelengths. You see here, this is an ALMA observation. These are HST observation. This is with VLT, and this is with ALMA. So this is ALMA in the gas and ALMA in the dust, right? It's a popular object. It appeared even in movies. Right? If you watch that movie, Don't Look Up, there is a scene here where they're looking at the computer, you know, for an observation they are doing. In the movie, they say that it's a galaxy, but no, that's a AB Auriga. So, yeah. All right. So what is the system here? This is the observation by Caris, and then the ALMA observation overlaid here in red. The blob is in here, right? This blob is at about 90 AU. This is the size of Neptune's orbit here. And this is to show that the object seemed to be moving, right, for the first observation done with Nikimus back in 2007, and it moved a bit here in this baseline in 2021. It's of course difficult to detect the movement when you are at 90 AU, right, because the motion is quite slow, but with this baseline of almost 15 years, some motion was indeed detected. Right. If you overlay both, then you see that you can convince yourself that there is some motion there of the source, which is compatible with Keplerian motion. Right. Right, and then they could calculate the orbit. I mean, they could constrain the orbit, find the most likely eccentricity and inclination. It seems to be compatible with an object of low eccentricity and you know, with an inclination compatible with the disk. There are other signs that this is indeed a planet. The fact that it has emission in H alpha. H alpha for planets is a sign of accretion, right? These planets are not hot enough to emit an H alpha on their own. If there is an H alpha emission, it's a sign of a shock that is happening on the surface of the planet. And then, yeah, you have an emission in H alpha, just like you would have in, in chromospheric emission in stars. It's a non-thermal emission coming from the accretion spot. Another sign here that this is a planet is that there is no detection in polarized light, whereas you have a detection in total intensity here. So not having polarized light here means that the light that you're seeing is not just scattering, right? The scattered emission will be polarized, whereas thermal emission will not. So there is a mix here of both. So this is a model. So this is a disk model in the H band. In the total intensity. So in this model here, you put a black body right inside the model, and then compute the radiative transfer through it, then to find out what the intensity will be. And this is the emission you get here of the planet in total intensity, and the amount that you get in polarized intensity. As you see, there is not much. So our interpretation for this is that what we're seeing here is a planet that is seen in thermal light, but through nebulosity. So an apt analogy in this case is like if you are seeing it, if you're seeing a lamp through fog, right? As you see a lamp through fog, right, it's going to look bigger and more diffuse than if you saw a lamp without fog. And what are the other constraints here that we can get to find out if this planet really is a gravitationally unstable blob or not? There are some constraints. For instance, there are these two observations here in different bands from the HST and ICMUS. So that constrains here the accretion model, right, from the planet. That is not a black body, but these two measurements here can be fit by a accreting planet model. The scattered light does not reproduce the continuum, but if you add them both, then you have this line here, which is the scaled intensity coming from AB Auriga itself. Right. So this is inconsistent with pure scattered light, but it can be reproduced by this model here, the blue model, which is a thermal source at about 2,000 Kelvin with a magnetospheric accretion at about 10,000 Kelvin. The luminosity, if you integrate all of the light that you're getting from the planet, it's about 2.5 times 10⁻³ solar luminosities, that if you constrain with the age of AB Auriga, so thank you folks for measuring ages for us, you find that this is consistent with a luminosity of about, with a mass of about 10 Jupiter masses. So the way that you do that is that you measure the luminosity, right? And you know the age, and then you go here from this tracks, and then you find out what is the mass, right, that you expect from this object. In this case here, a luminosity of about minus 2.5 for the age of AB Auriga falls into the track of about 10 Jupiter masses. So what we have here is an object, what we have here is an object that the colors are suggesting a temperature of 2300 Kelvin, right? And the model suggests a mass of 10 Jupiter masses. So we have two possible ways to form this. One is by core accretion, but the other one is gravitational instability. And when you look at what AB Auriga looks like, what the disk around it looks like, this looks like what you expect from a model of gravitational instability. There is also evidence that this is a massive disk. So everything seems to point towards that. Another thing is that if you are seeing this planet through fog, that means that the optical depth must be close to 1, right? So the optical depth is this quantity here, right? The combination of opacity, density, and the length. In this case, then would be the scale height of the disk. If this is 1, right? If the optical depth is near 1, then you have a measurement of the density, right? So if you play this game, if you know what the opacity of the gas is and the scale height of the disk, which you know given the temperature, you find that the density is about 10 to the minus 12 grams per cubic centimeter. Integrate that in height, you have a column density of 3 grams per square centimeter. And why I am bothering you with these numbers? Because we talked about the Thornbury Q value. If you have a measurement of the column density and you know the temperature in the disk, you can measure what the Q value is. You fit then that into a disk model, and this is what you find here for AB Auriga. You find that the Q value is indeed lower than 1, like less than 1, between 50 AU and about 150 AU. So this is a sign then that the disk between 50 and 150 AU is indeed gravitationally unstable. And that's squarely where we find this object that could be a gravitationally unstable planet. Not only that, that the disk goes again to be stable beyond 150 AU matches what we see here from the ALMA observation. So you have gravitational instability inside in this region, and then you have that the disk is stable beyond 150 AU. So that explains both the observation of the blob and the disk being gravitationally unstable, and also this regular ring that is seen with ALMA. Right? So it looks pretty good, pretty convincing. And I was curious enough then to run a model, right, to find out if this disk would indeed form planets or not. And this is what came out of the model. As you see, there's not much showing on there. But that's because we're plotting here linear density. You see the scale of the density here goes like hundreds or so. So you have this little blob. Of course, plotting in logarithm, then you see a lot more structure. Again, the inner part being gravitationally unstable, right? And the outer part being gravitationally stable. So that's the density, and then you measure also the temperature. That's the scale height that you get from the disk. You pass this through a radiative transfer code, and this is what you get, right? So again, doesn't look much, but if you take this image and if you rotate it to the orientation of the disk, this is what you get, right? So it seems that the main features are there, right? This region here matches this region. You have this ring around here. You can see more or less the same thing. There is this inner part here, right? This blob here too. I didn't even try to make it match that well, but you know, it just came out in this way. So that's pretty good. And then you take this model and you add a source to it. So there is a hidden source in this disk. So this is a model of the star plus a gravitationally unstable blob, and the model of the star itself. You subtract them both, and then you find here the planetary source in the end. So this seems to match then what we expect from this disk. So HR 8799, that's the one that I showed before, right, with those planets that are orbiting there. And AB Auriga B, they seem to be our best bets for planets that are formed with gravitational instability. How much time I have left? 10 or 15 minutes. Good, good. So let me change gears a bit. So now we know how to form planets, it seems, right? We covered a lot of ground here on these 4 lectures so far. We passed from the dust, right? You start from an interstellar dust, you grow them to pebbles, and then there is a mechanism to form the first planetesimals, right? And then the planetesimals collide with each other, accrete the remaining pebbles from the disk to form the rocky planets, or then you can form the gas giants through direct gravitational instability of the gas, right, through this mechanism. And that seems to explain most of the features that we find in the solar system. However, when the first exoplanet was found, you may remember that there was a little surprise there, right? That doesn't seem to be fit then by everything that we have studied so far. So, remember from the very first class, right? On Monday, I said what the general idea for the formation of the planets was, right? You have that there is a snow line somewhere in the disk, so that the objects that you form are going to be ice poor in the inner part and then ice rich on the outer part. There is more ice, so then the things that are formed outside end up being more massive because there is less material, right? So in the inner part, you form rocky planets. On the outer part, you form icy planets. And if they get big enough, they end up becoming giant. So that explains neatly the dichotomy that exists in the solar system of small planets inside and bigger planets outside. And then comes 51 Peg, the first exoplanet. Surprise, surprise. This is the Sun and Jupiter, and this is 51 Peg. It's like a super Jupiter. I mean, it's a Jupiter-sized planet, very close to the star. So the existence of hot Jupiters through water on this possible explanation. But this surprised the observers, but not the theoreticians, because planet migration was not new. Planet migration had been suggested 15 years before the discovery of the first hot Jupiter and the first exoplanet. And seems that the most typical planet in the galaxy is actually at a 3-day orbit. So this is the diagram, right, of all exoplanets known. And if you see here, if you plot a histogram of the distance, this is where all of the exoplanets would fall there. You have here this pile up at 3-day. Oh, I thought I had updated the figure this morning. Sorry, this is showing here from 2020. But yeah, a new figure that I pulled just this morning is also showing the same thing. So there is evidence all over the place that planets migrate, right? They don't end up in the same location where they are born. First, the existence of hot Jupiters, right? This 3-day pile up, planets very, very close to the star. And also around the sun too, you find objects that are in very special orbital configurations, like the moons of Jupiter, right? Europa, Io, and Ganymede, right? For every orbit Ganymede does, Europa does 2 orbits, and for every orbit Europa does, Io does 2 orbits. So it's a very special orbital configuration that does not arise naturally, right? If the planets were formed, or in this case, these moons were formed at this. I mean, they didn't form in this orbital configuration. They were moved. They got to this orbital configuration somehow. This orbital configuration is also found among exoplanets. Right? Kepler 223 here has 4 planets that are in special orbital configuration too, locked in an 8643 resonance. Right? And when you look at several exoplanetary objects in the exoplanets found so far, you find that several of them are in resonance. You see, there is a pile-up of planets at these resonances. So this shows here that the planets are migrating, right? And let me tie that also with the theme of this the school, which is to connect the gravitational waves with planets, right? So how do we combine the gravitational waves and planets? Well, there is a class of objects that is very alike to protoplanetary disks, which are AGNs, right? Active galactic nuclei. So the AGN channel for the production of black hole mergers, what Filippo and well, what Filippo has mentioned in his classes, and Alessandro also will talk more about that next week. So I'm just going to give a quick primer about this. So you're going to hear more about it next week. The idea then is that there are several objects that are orbiting in an AGN. So they're quite like planets, protoplanets orbiting in a protoplanetary disk. So if we think that you form planets by merging planetesimals, right? The same process should be happening also in AGN disks. But instead of merging planetesimals, you are merging stellar mass black holes. When you look at the mass ratio between the sun and planetary embryos, it's pretty much the same mass ratio between the supermassive black hole in the center of the AGN and stellar mass objects orbiting in the AGN disk. Right. So the motivation from this came from LIGO, from the first set of observations, right, of LIGO, showing that some of these mergers had masses that couldn't be explained by stellar evolution alone. So you have black hole mergers that are too hefty, right, to be produced in this way. So maybe they come from second generation mergers, right? You merge small mass black holes, make bigger black holes, and then they keep merging, just like planets do when they are growing. So that led to the idea that you could use the physics of protoplanetary disks and scale them up to AGN disks. So essentially, that's borrowing physics, right? Instead of planet migration, then you would have a black hole migration. So let me explain a little how this migration happens. You form a planet in a disk, and it is born around all of this gas, so it is going to suffer torques through the gas, right? Planets form, and they start exchanging angular momentum with the disk. You can calculate exactly how this angular momentum exchange will happen. You have here the arm, right, and the force. The arm here is the orbit of this semi-major axis of the orbit of the planet, and the force, of course, is the gravitational force. So place here the force, right, that you get from gravity, and then you have what the angular momentum exchange will be. You integrate this, right, and then you find here what the combined torque will be. There is something that you can immediately see here. The torque has an anti-symmetry. Y here is the coordinate, right, on the opposite side of the arm, right? That is perpendicular to the arm. There is a symmetry with respect to the arm of the planet. That means that the torques that are on the upper part of this plot here will contribute positive torques, and the part that is under here will contribute negative torques, right? That's just because of this y here. So in this case here, I showed it in Cartesian coordinates. This is in cylindrical coordinates. So this sign here is going to be positive on this part, but it's going to be negative, right, on this part of the diagram. So if you have axisymmetric densities, which is in this case here, this integral is going to give you 0. So the way to make a planet migrate is to break the symmetry. Luckily, that's exactly what planets do as they're orbiting in a disk. So this is a simulation of a planet orbiting in a disk. As you can see, the planet is executing orbits and then exciting this spiral density wave. This spiral density wave is breaking the symmetry of the disk. So in principle, the torque doesn't cancel anymore. You have to now compute the torque, taking into account the fact that a planet, as it's orbiting the disk, generates a wake in the disk. And this wake is not symmetric. So this wake of the planet in the disk analogy here is like these waves, right? That things in water make as they travel through it. This V-shaped wave. In English, sometimes they call this duck waves, because like you see them with ducks, like as they, I mean, in Europe, right? They have often canals with ducks, so everybody sees them, every day. So maybe that's why they called it in this form. It's memorable, connecting with something that people see every day. So this is the same wave here, but in a boat in the ocean, this V shape, right? Now, in a disk, you don't have a V shape. You have the two arms, right? One that is beyond the planet and one that is behind the planet. That's because of the shear, right? That's because of Keplerian motion. If you take here this boat, right, and this wave, and then you add now the Keplerian motion, this part would be overtaking the boat, and this part would be trailing the boat. So that's the origin of the asymmetry. If you look at the wake that the planet generates, but now in a system that is following the rotation of the planet, that's the shape that you get. The shape is stationary in a frame that is moving with the planet, right? So that's just like that V-shape wave, but now you add here the faster motion in the inner orbit, so then the wake will overtake the planet. Now you compute the torque with this, and you find that there's going to be a small asymmetry, right? The symmetry now is broken, because you have now a density wave on the positive side here, on the upper part, and have this wave here on the negative side of the torques. It doesn't look much, I mean, it doesn't look like it changed much when you plot the torques, but if you zoom in onto the planet, this is how the migration torque now looks like. You can clearly see here the positive contribution of the inner wave and the negative contribution of the outer wave. You have to compute both, subtract to see which one wins. Right. And I'm going to give a spoiler. The outer one wins. The torque is negative, so the planet loses angular momentum and then moves inwards. So this is a migration here. Apparently it's not. I don't know why it's not showing. Oop. Okay. Hopefully this will play. No. All right. Just a big orange square. Okay. The movie is not showing. Well, what this movie would be showing, it would be the wake of the planet, and then maybe it's just buffering, and then it migrating inwards. Apologies for the movie not working. Right. So what is causing this here? This is caused by Lindblad resonances. What we're looking at here when a planet is migrating is the response of the planet on a disk. You have here a simulation where you had the planet, right? This is now plotted in radius and in azimuth, in cylindrical coordinates. What you're seeing here is the response of the planet in the disk. When you plot here some major axis versus eccentricity, you clearly see here these regions, right, where the response of the planet on the disk is maximized. These are in the location of resonances, right? We call this Lindblad resonances. These are locations where the interaction with the planet is maximized. The location of these resonances are calculated by this, right? So m here is an integer. Omega is the frequency at a given location in the disk, and omega p is the frequency of the planet. Whenever you have this quantity here matching, like matching what you see here in the right-hand side, when integer m's lead to this quantity, right, matching what you see here, then you'd have locations of increased response. So the locations of the Lindblad resonances will be given by what you see here. When you plot that in regions of the disk, you see a concentration around the planet. So m equal 1 is here. The m equal 2 is on this location and on this one, right? And as you go inwards more and more, they would pile up at the location of the planet, right, as the m goes to infinite. Well, that's not good, because you don't want them coinciding with where the planet is. But we have that the disk is made of gas. So what we didn't consider here in this was the pressure. If you include the pressure, it turns out that there is a cutoff near the planet, which is given here by the pressure scale height, that quantity h that we talked about before. So now they will pile up, but they are going to be at a finite distance from the planet. This region here, where the resonances pile up, is where this Lindblad resonances, where the wake is launched. And as you see, turns out that the outer one is a little bit closer than the inner, and that's why the outer one wins, because it ends up being closer to the planet. All right. There is an asymmetry in the location of these resonances, so that the outer Lindblad resonance is closer to the planet for the same value of m. The outer one wins, and then the planet migrates inwards. Right. So you compute torques here for the inner and the outer one wins. You have inward migration. Now, there is another symmetry break here when you consider the thermodynamics of the disk. Right? The migration can be either inwards or outwards, depending on the thermodynamical response. These are the torques that you get for an isothermal. That's the case we've been considering. Then, in this case, the torque is always negative. But you can see here the torque can flip positive if you go to radiative simulations. And what is going on here is that the disk has an entropy gradient, right, around the planet. So as you have co-rotating orbits near the planet, you can have an excess entropy in this inner part here, as the gas comes from an orbit that has more entropy, right, to this area. So if the entropy goes up, then the density will go down. And then on this case here, you have a deficit of entropy. So this side here becomes over dense. So that's another way to break the symmetry. And in this case, right, if it becomes over dense here and then under dense there, you flip what we had before, and now the inner torque wins, and you have then that the planet can migrate outwards. So that leads to the emergence of the possibility of migration traps, that if you have a positive torque inside of a given region, then the planet will migrate outwards. But then on the outer part, you have a negative torque, so the planet will be migrating inwards. So it will be trapped in this region here where the torque is 0. So a migration trap is a region of 0 torque with a positive torque inwards and a negative torque outwards, so that from both sides, you're pulling it towards a region of 0 torque. We call these migration traps. All right. So what you see here are migration tracks of possible planets. Planets that you put in the disk of different masses, and you see that they move towards this region of 0 torque and stay there. Inside here, the torque is positive, so moving outwards, and then outside the torque was negative, so then it moves inwards. If on top of it you put that there is an overall evolution of the disk migrating outwards, then you end up with these migration tracks here. So as a rule of thumb here, so if you put here the disk evolution, so this is the evolution of the disk in time, right? The density will go down, the temperature also is going to get colder. So as a rule of thumb, migration is outwards if you have steep temperature gradients, and inwards in more isothermal regions of the disk. So you have here isothermal regions, an isothermal region there, more isothermal, and steep gradients in some areas of the disk. That leads then to the emergence of these two migration traps. And you can also end up having like resonant convoys, because the first planet that gets to the trap sets up the resonances, and then everything migrates inwards as a resonant convoy. And if on top of that, you also add the gravitational interaction between the planets in this calculation, you end up with this giant mass, right? So one planet goes there, sets up their resonances, traps the other objects in resonances, and they merge. They go merging, 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 and then in the end, you end up with like 3 massive objects here. In this case, each one of them had about 10 times the Earth mass. And then everything then migrates inwards. Right. So we applied this idea then to AGNs. And what we saw then is that, yeah, indeed, this would lead to the formation of migration traps around black holes. Oh, sorry, around supermassive black holes. So you have here 2 different AGN disk models that are widely used in the literature. This is the Circle-Goodman model. You have here the temperature and the scale heights of this, and the TQM model, right? And we calculated them where the migration traps should be in these cases. Turns out that the Circle-Goodman model has 2 migration traps. So this is here the torque in linear scale, and this is in log scale. You can see here regions where you have what I mentioned, right? A region where you have a positive torque inside and a negative torque outside. So this is a migration trap, and this is another migration trap. They are at about 25 and 300 gravitational radii in this model. And the TQM model has 1 migration trap, which is here at about 245 gravitational radii. When you put orbiters inside the disk, yeah, they quickly migrate there to this trap, and you have those same gravitational interactions that we saw in protoplanetary disks, and then they form a binary when they reach. Okay, I will stop now, and I will take questions. So, thank you.
Wladimir,
Yes.
it is possible to predict for a given protoplanetary disk parameter, for example, if the migration will take place?
Right. Yes. Short answer is yes. We can predict that based on our understanding of migration. As I said, we know how to calculate the torques. Right, the torques are a function of the density gradient and the entropy gradient and other gradients in the disk. So in principle, you have all of the ingredients that you need to calculate the torque if you know these quantities. I'm putting here again the image. Yeah. So it's just this, right? You calculated the torque by evaluating this integral. This integral depends only on quantities that you know from the disk, right? From the model. However, that's a tricky game to play because there are so many other things that can lead to changes in the density. Because as you can see here, most of the torque arises from a region that is very close to the planet, right? So anything that changes the density near the planet will impact the torques. In this field, I mean, being in this field for like 2 decades, it seems that every year there is a new ingredient in the model that changes the magnitude of the torque or even the direction. If you include thermodynamics, it will impact the torques. If you include the magnetic fields, it will change the torque. Like, you know, it was also found recently that if you include the luminosity of the planet, that will also impact the density, right, of the gas near the planet, and also have an impact on the torque. So long story short, yes and no. If you are given the disk model, you can calculate what the torques will be, but the situation is extremely nonlinear, right, and can change with the ingredients that you put in the model. So in the end, you need numerical calculations to find what the torque is. And one thing about numerical models is that we cannot put all physics in them, right?
Well, this might be a bit, it's probably very, very far-fetched, but on AGNs we have, we kind of can see traces of the dynamics in terms of the variability of the AGNs, but I'm not sure, maybe these are such small scale, you know, granular stuff that cannot possibly be connected to what you're saying here, but in some sense, the some of these clumps, they have to eventually fall in and feed the central black hole. So, is there a way to connect these things?
Right.
It's probably a very naive question.
No, it's not naive at all. It's actually a great question, and thanks a lot for asking that, in fact, because this could be one of the ways that we can tell if this works or not, because the other channels for merger of black holes not always lead to electromagnetic counterparts. But if the merger happens in an AGN disk, you have gas, right? So you will have EM counterparts. We are working actually, I have a student working on this to use our models, right, of mergers in AGN, pass them through a radiative transfer code to figure out what the light curves of these events will be, and see if we can match what some of the observations show. The difficult part of it is actually to find, to determine if an AGN event really coincided or not with a gravitational wave event. Right? That seems to be one case where after a gravitational wave event, there was an AGN flare in the same, in the general location of the gravitational wave event. We are using that to see if we can run a model, if we have a model of black hole mergers in AGN that could reproduce that.
Yeah, I can also add a bit more on this. I will talk about AGN channel next week, but in regards to electromagnetic counterpart, it's very difficult to outshine the AGN. So that's the main challenge of these models. Yeah, and there was a recent study. So, of course, the sky localization of events at the moment is very poor, like 100 degrees squared on the sky. But you can do statistics with many events. And there's been people from Leiden who did publish a study in trying to correlate the GN distribution to the cumulative distribution of black hole merger events. And they basically find that they do not correlate, or rather, the events do not correlate with the most massive AGNs, the most massive black holes, which is actually agrees with the theory so far, because we don't expect that the
They're
massive...
brighter. Yeah, because the more massive AGN will be brighter too. So it's harder to outshine them.
Yeah, and they won't have traps. So more massive black holes won't have disks. I mean, they will have disks, but without traps.
No. Right, but there is another point too about these migration traps, right? Sure, you can use the theory that is being built for protoplanetary disks, right? You see here, you have a planet, you have the dense waves, and then you transport it to AGNs and say that the same thing should happen there. However, there is a major difference here when it comes to AGN, is the fact that in a protoplanetary disk, you only have a few objects, right? But when it comes to an AGN, the nuclear cluster is very dense. You have like 100,000 objects there. So how will crowded migration look like? Already when you put a few objects, this is what you see, right? You have overlapping waves. So this clear cut, like type 1 migration, will change when you put like 100,000 objects, right, in it, and then predict what their migration tracks will be. Because you have overlapping waves. We still need to build a theory about how crowded migration looks like. Is it like simply adding the spiral wakes from the individual objects? And this thing will start to break down when the co-rotation regions start to overlap. You need to get them very close to one another. But if I have 100,000 objects, that will happen.
I have a question, sorry. At some point, I had the impression that you wanted to correlate migration to mass ratios of black hole. No? You listed the masses.
Right.
But
Correct.
then you dropped the idea, then I didn't see any follow-up.
Right, okay. Sure, yeah, there is a difference between what we call type 1 migration and type 2, which depends on the mass ratio of the planet and the central mass. What happens is that if you have that the mass ratio, oh sorry, that's not this one here. If you have that the mass ratio is such that the planet carves a gap, you enter in what we call the type 2 regime. Sorry, this is for low mass objects. Where is my slide here? Right. Sorry. Right. So this is how this planet interaction happens, right? This is an embedded planet. Embedded planets are the ones that are so low mass that they don't carve gaps. But if the planet gets massive enough so that its heel radius becomes bigger than the scale height of the disk, it will carve a deep gap. So that changes the migration. So the way that I was connecting the mass ratio to this was in this way. Yeah, we can apply type 1 migration, which is for low mass objects. But if you start building intermediate mass black holes, at some point they will become massive enough and may carve a gap in the AGN disk. Right. So there is no evidence, as far as I know, about gaps in AGN disks. But if they are found, yeah, there could be a telltale sign of the formation of intermediate mass black holes. At least for the scale heights that we have in protoplanetary disks, that transition is at about mass ratio 10 to the minus 4. So for a supermassive black hole, a mass like 10 to the 8 solar masses, we're talking about building something of 10 to the 4 solar masses in the AGN disk.
Which had never been observed yet.
Never been observed yet. These are intermediate mass black holes, yes.
Okay.
There we go. That was the slide that I was looking for. Yes. Yeah, this is the embedded planets, type 1, and these are the gap opening planets, type 2, migration. Yes.
Yes. Can this migration of the planets that you're talking about also explain some planets that don't have host stars?
Right, rogue planets. Yeah, rogue planets, you wouldn't explain them through gas migration because the migration would not unbound. I mean, they would not unbind the planets, right, from the star. To explain rogue planets, probably you would need scattering, right? Planet-planet scattering, like three-body interactions. You have two massive planets. If they get very close, one of them, can slingshot the other planet. So you would need very massive planets, but in principle, yeah, like that's possible. The other idea is that perhaps rogue planets are just formed like stars, the same way brown dwarfs, right? Star formation doesn't know about a hydrogen burning limit. Star formation doesn't know about deuterium burning limit. There is no a priori reason why the gene's mass should not overlap with planetary masses. So yeah, so rogue planets could be formed either by this. They are formed in a disk and then kicked out, right, by three-body scattering, or they can be formed by direct gravitational instability from the same cloud that formed the other objects. We don't know yet which mode is the main one.
Yeah, so in Copenhagen, we have some planet people that are very skeptical about the AGN channel, and I will repeat their question to you. So, so if you say black holes, they meet in AGN disk and form binaries, why we don't see binary planets?
We see binary planets, the Earth and the Moon.
But
It's a binary planet. Pluto and Charon, it's a binary planet also. It depends on your definition of planets. I like to call planets anything that is round, right? That has enough mass to shape itself in a sphere. So in this case, Earth-Moon system is a binary planet. So is Pluto and Charon. But I guess that's what you're getting with your answer is that why don't you see pairs of Jupiters, right? Well, people have been looking, right, for objects like that. In fact, Dave Keeping claims to have found. He was originally looking for moons, right? That's his main thing, and he found an object that is a super Jupiter planet with a quote-unquote moon of Neptune mass. Would you call it a binary planet? I mean, I would. And also the fact that when you are in an AGN disk, you also have the extra component of gravitational waves. So if they get very close, like gravitational wave emission will harden the binary. Of course, you need to get very close for it to happen. But another place where you see binaries is in the Kuiper belt. The Kuiper belt is full of equal mass binaries. And these are actually more akin to the mass ratio that you have between supermassive black holes and stellar mass black holes in AGN. So they're wrong.
Tell them that Vladimir told them. Okay.
Thank you, everybody.
Going once.
Oh, yeah. Do you have more questions? Oh, yes.
Okay, I mean, migration is accepted, right? It's a well accepted thing in the community. That is true. But migration has some problems. I mean, stability is one of these problems, right? To immigrate, you have the stability that is arriving. So what about migration, non-migration at the same time? So some planets are in situ, all are not. So just for the students know that that is not completely accepted, right? Some exoplanets could migrate, and other is just born over there. I talk about Jupiter, right? So this hot Jupiter can be close to the star and not migrate as well. So what do you think?
Well, let me use the buzzword that you like, metallicity.
Sorry, it's depressive plot.
Yeah. Well, let me see here. As I said, migration will usually happen, right? There's really hard to escape the conclusion of angular momentum conservation, right? So if people want to doubt migration, they have to doubt Newton, they have to doubt Gauss, right? So which one is right? But what I want to say with that is for all our understanding of physics, a planet forms and it will exchange angular momentum the gas. Now, the magnitude of this angular momentum exchange will determine how fast and how far the planet migrates. There are some situations where the migration can be quite small, right? It actually goes with the square of the planetary mass. So very low planetary masses will migrate very slowly, right? The more massive it gets, indeed, yeah, the faster the migration is, which is something you see here on this track, right? You have here these objects, right? They're formed at very low mass, and it's only when they build enough mass that they start migrating in. The metallicity here matters because it changes the thermodynamical response of the gas, right? So you can have different tracks in different metallicities. And as you see, you don't need to change it by much, right? From minus 0.4 to 0.4 to change the behavior completely, right? And we are not sure, we don't know, we don't have any evidence that Jupiter formed where Jupiter is now. It's completely plausible that Jupiter formed at 25 AU and migrated inwards. We don't know where it formed. But people are doing planetary formation and migration models to try to reproduce the population observed of exoplanets, right? So these are models that, I'm trying to find the slide here, that the community has been doing for a long time, right? First time that these planetary formation plus migration tracks were made, they did not reproduce, here, yes, the distribution of exoplanets at all. But, you know, like, the more and more we understand the formation and migration, we keep updating this plot. So ultimately, any comparison between migration theory and exoplanets cannot come from one single object, right? I mean, it must be statistical. So you take this plot and then compare with the distribution of exoplanets.
The problem is we have models
Yes.
against one Jupiter with 11 years optical period, right?
Right.
There is no all the planets like that. So we have only Jupiter in this position, in hundreds of hot Jupiters.
Uh-huh.
So we need to try to observe another Jupiter in these 11 years or 10 years optical to take some, a more concrete observational basis for that. By the way, it's just
there are Jupiter-sized planets in Jupiter-sized orbits, no?
with
Am
10 years
mistaken?
ops, our Jupiter is 11 years, right? I mean,
Well, 12, yeah.
12,
But
yeah. It's like,
wait a minute. Where's the distribution of exoplanets? There we go. Well, if you see planetary masses versus orbital period, right? Jupiter would be here, and one mass, yeah, I mean, like, it's a crowded place there.
I see a desert
Yeah.
over there.
Sorry?
Jupiter is 11, a desert. I mean, the
A
Jupiter
desert? Really? I don't see. So 10 years would be here, right? Sorry, no, here. 300, that's here,
so
here. Yeah, that's days, yeah. So 3,000 days, yeah.
no
10
planets.
years period, yeah. It's a 12-year period, so about 3,000 days here, and Jupiter is here. So it's in this region here.
3, right? 100 of planets over
Yeah.
there. So.
3 is a crowd.
Okay. Let's thank
Thank you.
Vladimir for all the course.